Okay, I think we are live now. Thank you, everyone. Welcome one more day to our PNS on processing in memory. Today we have another invited talk from Geraldo. Geraldo Francisco de Oliveira is one PhD student in the Safari research group. He joined the group in 2017, and since then he has been doing a lot of amazing work in processing in memory. He is the first author of this paper, this work that he's going to present, DAMOVE, a new methodology and benchmark suite for evaluating data movement bottlenecks. And he is also one of the lead authors of another important recent work on processing using memory, which is called SynDRAM. You may remember it from one of our previous lectures. So, Geraldo, if you're ready, please go ahead.
Thanks a lot, Juan. So, hello, everyone. Welcome to this week's PNS class. As Juan said, today I'm going to talk about this work that we did together here in Safari called DAMOVE. So, feel free to ask any questions on YouTube. We are going to stop from time to time to answer the questions when appropriated. So, I'm going to get started on DAMOVE. So first, here is just an executive summary of what is DAMOVE. So the problem that we are dealing in this paper is that data movement is a major bottleneck in general. So I think we've been talking about data movement as the bottleneck for a while in this PNS class. However, even though we have these amazing mechanisms to alleviate data movement, it is still unclear how different sources of data movement bottlenecks appear in a particular application, or the most suitable data movement mitigation mechanism, suitable here meaning caching, prefetching, or new data processing for a particular type of data movement bottleneck. Therefore, the goal of this work is twofold. First, we want to design a methodology that can allow us to identify the different sources of data movement bottlenecks in a particular application. And second, we want to compare how compute and memory-centric data movement mitigation techniques can alleviate such data movement bottlenecks. To do so, we perform a large-scale application characterization to identify which key metrics can reveal the sources of data movement bottleneck in a particular application. This work makes the following contributions. First, we do a large-scale experimental characterizations of over 77,000 functions across 345 different applications from varying application domains. Second, based on this experimental characterization, we develop a new methodology that can characterize the applications based on the data movement bottlenecks, their sources of data movement bottleneck, and also how these data movement bottlenecks correlates with different data movement mitigation techniques. Based on all of that, we provide DAMOVE, a benchmark suite with 144 application functions that can be used to study different data movement bottlenecks and data movement bottlenecks mitigation architectures. And also in the paper, we provide 4 case studies to highlight how you can use DAMOVE to solve open research problems. So DAMOVE is open source and is available in this GitHub link that is in the screen. So here's the outline for this talk. First, I'm going to briefly talk about the data movement problem and why we need a new methodology to identify data movement bottlenecks. Second, I'm going to provide our methodology. And third, I'm going to provide, so our methodology has 3 main steps. I'm going to go through each step in detail. So the first step is application profiling. The second step is locality-based clustering. And the third step is memory bottleneck analysis. And finally, I'm going to conclude with some case study. So I don't have it here in this in this outline, but after I conclude the talk, I'm going to give a quick tutorial about the DAMOVE benchmark suite and how we can use it. So let's get started with data movement bottlenecks. So data movement has become a bottleneck in modern systems for a couple of reasons. So first, because many applications does not have enough data locality. And if application does not have enough data locality, it's going to make ineffective use of the cache hierarchy. Second, DRAM or the main memories often cannot provide enough memory bandwidth for data-intensive applications. And third, because applications or systems cannot tolerate the high average memory access time caused by the frequent access to main memory. So high-performance computer systems have evolved over time to include mechanisms that can tolerate or can mitigate the impact of data movement bottlenecks or data movement in a system. Such mechanisms can be seen as a deep cache hierarchy from L1, L2, L3, or even L4, depending on the system, or aggressive hardware prefetchers. We refer to such mechanisms as a compute-centric architectures. However, such mechanisms not only come with large area cost and complexity, but often they often fail to mitigate or hide the latency and energy costs of accessing DRAM in many modern and emerging applications. To solve this problem, one promising techniques that aims to alleviate the data movement bottleneck in modern applications are the so-called memory-centric architectures. In such architecture, the cost of data movement bottlenecks are alleviated by moving or placing computation nearby or close by the memory device itself. Near data processing, or NDP, is a good example of such a memory-centric architecture. So in an NDP system, the cores that are placed nearby the DRAM has access to memory with abundant DRAM bandwidth and also a shorter average memory access time, which can accelerate the memory-bound applications. So therefore, the main goal of near data processing is to mitigate data movement bottlenecks in data-intensive applications. So near data processing is not a new idea. In fact, the data processing architecture has been around for a while, there are research proposals that date for more than 5 decades ago. However, only recently, industry have introduced the first near data processing architectures. First, one example of such architecture is the UpMem architecture designed by the company of the same name. The UpMem architecture integrates a large number of simple CPU cores nearby DRAM chips, targets the acceleration of general purpose computing applications. So the UpMem architecture can provide a peak throughput of 0.9 teraops per second. Another example is the Samsung film DRAM architecture, which are similar to the UpMem architecture, also integrate some processing elements nearby the DRAM banks, targeting the acceleration of neural network device or neural network applications. This film DRAM architecture can provide a peak compute throughput of 1.2 teraflops per second. So the UpMem architecture has been explained in several meetings here in this PNS class. If you want to know more details about the architecture, how to program and how to use it, you can see the PNS pin meetings 2 and 3 in this YouTube link. And also, if you want to know more about the film DRAM architecture proposed by Samsung, you can check the PNS in meeting 4. So the question that arrives now is, when should one employ near data processing? So we know that near data processing can be employed for applications ranging from graph processing, mobile consumer workloads, neural networks, DNA sequence mapping, databases, time series analysis, and many more. All of these works rely on many different methodologies to identify memory bottlenecks in a system. Often such methodologies are intuitively used as indication of NDP suitability for a particular application. However, as I will show next, none of those models are comprehensive enough to identify memory bottlenecks and NDP suitability. This happens because those models are built targeted to identify specific sources of data movement bottlenecks, and often their definitions of compute and memory bound are not enough to indicate NDP suitability. In this talk, I'm going to give 2 examples here that are commonly used to identifying data movement bottlenecks and also to identifying NDP suitability. So the first one is the so-called Roofline Model, and the second one is identifying applications with high level cache misses per kilo instructions. So first, let's get started with why the Roofline Model is not good enough. So a Roofline Model is a simple model used to identify if an application is memory bound or compute bound. In this model, the x-axis of the plot defines the arithmetic intensity of an application, calculated as the number of operations the application executes per byte it accesses. And the y-axis shows the performance of the applications and giga operations per second. If an application fits below the compute roof model, compute roof line, which is defined as the peak system throughput of the system that you're evaluating, we call that this application is compute bound. Applications below this curve or compute bound applications are often called not suitable for process memory offloading. The second line in this model is called the memory roof. It is defined as the maximum DRAM bandwidth times the arithmetic intensity of the application. Prior works have shown that applications below this curve are memory bound and are suitable for NDP offloading. We use this model with more than 40 applications that we're going to analyze later. We compare when such application benefits from a general proposed NDP architecture. In the plot, we classify the application as runs faster on the CPU compared to running on an NDP system, run faster on the NDP system compared to running on the CPU, has similar performance on the CPU on an NDP system, or depends. When the performance of the application depends on some particular system configurations, as for example, as the core count. Based on that, we make the following observations. First, memory-bound applications benefit from MDP, as prior works have indicated. Likewise, compute-bound applications do not benefit from MDP, also as indicated by prior works. However, we observe that there are some memory-bound applications that can also not benefit from MDP or benefit from NDP in a particular configuration, as for example, at different core counts. Likewise, this behavior also happens for compute-bound applications. Therefore, we conclude that the Roofline model cannot currently identify when an application is suitable or not for NDP offloading. Next, we analyze another metric utilized to indicate NDP suitability. Many prior works have said that applications with high less level cache misses per kilo instructions, usually have a higher value larger than 10, benefit from new data process. We check this observation by evaluating the speedup provided by NDP on a large number of applications here in the y-axis, and the application MPKI in the x-axis. We make the following observations. First, applications with high MPKI are always faster on NDP as predicted by prior works. Second, applications with low MPKI are always faster on the CPU baseline, also as predicted by prior works. However, we also see applications that have low MPKI that can run faster on the NDP system or have similar performance on the CPU and NDP system, or the performance depends on some particular system configuration, again, as core count. Therefore, we conclude that the misses per kilo instruction alone is not currently enough to identify when the application is suitable or not for NDP offloading. Therefore, to summarize, different approaches used to identify memory bottlenecks and NDP suitability are not comprehensive enough in identifying different types of data movement bottlenecks and also correlating these different data movement bottlenecks with different data movement mitigation techniques as NDP. Therefore, the goal of this work is to develop a methodology that can identify the major sources of inefficiency that leads to data movement bottleneck by observing and identifying relevant metrics and comprehensively compare traditional compute-centric and memory-centric data movement mitigation techniques to more memory-centric techniques, thereby developing a rigorous understanding of the best techniques to mitigate each source of data movement bottlenecks. Next, I'll give an overview of our workload characterization methodology. So we develop a new workload characterization methodology that can identify the data movement bottlenecks in an application and the suitability of these of different data movement mitigation techniques on alleviating such data movement bottlenecks. To do so, we leverage two main profiling methodologies. The first one is architecture-independent profiling methodology that provide metrics that can characterize the application memory behavior independently on the underlying hardware. And the second one is architecture-dependent profiling that evaluates the impact of the system configuration, as for example, the cache hierarchy, on the memory behavior. Our methodology has three main steps. First, it takes as input our application source code and its input dataset. In the first step, we use a hardware profiling tool to identify memory-bound functions across many applications. This step allows for a quick first-level identification of many applications that suffer from memory bottlenecks and functions that cause those memory bottlenecks. Second, we utilize a new simulator called a MoveSim to collect key metrics and execute performance analysis of the functions we identify in the first step. In the second step, we use the architecture-independent profiling tool to collect metrics that can provide insights about the memory access behavior or the memory bottleneck functions. In the third step, or step 3, we collect architecture-dependent metrics and analyze the performance and energy of each function application when each one of our 3 candidate data movement mitigation mechanisms is applied to the system. By combining all of this data from these 3 steps, we can systematically classify the leading causes of data movement bottleneck in an application or function into different classes of data movement bottlenecks. So I'm going to go through each one of these steps in more details, starting with step 1. The goal of the first step is to identify applications or application functions that suffer from data movement bottlenecks. To profile the applications and identify functions that suffer from data movement bottlenecks, we use a hardware profiling tool. In this work, we decided to use Intel vTune. Intel vTune provides a metric called memory bound, which is defined as the percentage of CPU pipeline slots that are not utilized because of memory stalls. Then I'm going to briefly give an overview of step 2. In step 2, we aim to analyze application memory characteristics as locality, thus you can understand how it affects the component of the memory subsystem, as for example, as the cache behavior or prefetching. To this end, we evaluate 2 key metrics. First, we evaluate spatial locality from application. For this, we collect a memory trace of application to build a histogram called stride profile, where each bin stores how many times each stride appears in the memory trace. In this example, the stride between the first access address and the next access address is equal to 1. Then we increment a stride profile histogram in bin 1 to indicate such a stride has been observed. We use the stride profile histogram to calculate the cumulative distribution of stride profiles, which represents the final spatial locality value. A spatial locality value close to 1 is caused by large stride values or random access patterns from applications, as shown in this example. In such case, a spatial locality close to 0. In such a case, we say that the application has low spatial locality. A spatial locality close to 1 is caused by sequential access patterns. In such a case, we say that this application had high spatial locality. Similarly, we evaluate how much temporal locality application has. For this, we collect the memory trace of application to create a histogram called reuse profile, where each bin represents the number of times a memory access is reused. For each memory address, we increment the bin that represents the corresponding number of repetitions. In this example, address A is reused 4 times. Thus, we increment the reuse profile histogram in bin 4 to indicate such reuse has been observed. We use the reuse profile histogram to calculate the cumulative distribution of the reuse profiles, which represents the final temporal locality value. A temporal locality value close to 0 is caused by low data reuse. In such case, we say the application is low temporal. So the application has low temporal locality. Application with temporal locality value close to 1 is caused by high data reuse. And in such case, we say the application has high temporal locality. Sorry. So based on that, after that, we go and take a look at step 3 of our methodology. While step 2 is going to allow us to understand the inherent application sources of memory bottlenecks from a architecture-independent point of view, it's also important to understand how hardware architecture features can also result in memory bottlenecks. As a result, in our third step, we perform a scalability analysis of the function selected in step 1, where we evaluate the performance and energy scaling for 3 different system configurations. The scalability analysis is use of 3 architecture-dependent metrics. First, arithmetic intensity, or AI, defined as the number of arithmetic and logical operations per L1 cache line access. This metric is going to show how compute intensive this application is. The second metric is the less level misses per kilo instruction, or MPKI, defined as the number of less level cache misses per 1,000 instructions. This metric is a good indication of how the memory intensity of a particular application. And the third metric is a metric that we developed in this paper called last to first miss ratio, or LFMR, defined as the number of less level cache misses per L1 misses. This metric is, as we're going to show next, is a good indication if an application benefits or not for the L2 and L3 caches, and also correlates well with NDP suitability. The goal of the scalability analysis that we perform in the third step is to nail down the specific sources of data movement bottleneck in a particular application. In this analysis, we evaluate the performance and energy scaling of application in 3 different system configurations and collect the key metrics for a bottleneck classification, those 3 metrics that I just presented before. During the scalability analysis, we simulate 3 system configurations of a Genome proposed multi-core processor. To this end, we build a new framework that integrates the ZSIM CPU simulator with the RowHammer memory simulator to produce a fast, scalable, and cycle-accurate on-processor simulator called the MUSIM. We use ZSIM to simulate the core microarchitecture, cache hierarchy, coherency protocol, and prefetchers. We use RowHammer to simulate the DRAM architecture, memory controllers, and memory accesses. In the first configuration, we evaluate a host CPU system which has a deep cache hierarchy, which is built with a private L1 cache of 32 kilobytes, a private L2 cache with 256 kilobytes, and a shared 8 megabytes L3 cache. The memory, this configuration access main memory or DRAM via off-chip link, which has limit bandwidth. The second configuration that we evaluate is of a near data processing system. This configuration, in this configuration, we move the general proposed cores nearby the DRAM chip itself, which enables for a larger bandwidth and shorter memory access time. This NDP system has a single L1 cache, a single L1 level cache, which has 32 kilobytes. In our paper, we evaluate a third configuration that includes hardware prefetches on top of configuration 1. However, we omit this configuration in this talk. It's important to say that the remaining components of the systems in both configurations remain the same. So the branch prediction in both cores in configuration 1 and configuration 2 are the same. For example, the pipeline depth, all of those microarchitectural details are kept the same. So we can identify exclusively the sources, the difference in performance caused by different data movement requirements from a particular application. For all configurations, we swap the number of CPU cores in your analysis for 1 to 256. Since prior works have shown that large core counts are required to saturate the bandwidth provided by modern high bandwidth memories. And because modern CPU and data processor proposals can have varying core counts, as we have seen in the UpMem system, for example. It's important to say also that we use as the main memory a 3D stack memory model after the hybrid memory cube or HMC device as our main memory. In this setup, the CPU cores in the NDP system are placed in the logic layer of the 3D stack memory and access the data, the DRAM or the 3D stack memory with the internal circuitry of the device. While in the configuration 1, in the host CPU system, the CPU access the data through the series of chip link provide the 3D stack system. Also important to say that the MUSIM is free and is open source and available in our GitHub in this link. So I'm going to stop for a second to see if we have any questions on GitHub, on YouTube.
Yeah, let me check. No, I cannot see any questions for now. I think you can continue.
Thanks, Juan.
Do you guys have any questions? Okay, probably no questions also in Zoom. Thank you.
So after giving an overview of our methodology, our 3-step methodology, we are going to now apply our methodology over a large range of applications. First, we are going to apply step 1 to identify memory-bound functions within applications. In this work, we analyzed 245 different applications from varied domains, from, for example, graph processing, neural networks, physics, high-performance computing, genomics, and many more. We observed that applications that benefit from MDP and suffer from memory bottlenecks have a memory-bound metric, which was provided by the Intel Vtune hardware profiler, greater than 30%, and takes at least 3% of the clock cycles of the execution of the application. Based on these criteria, We find 144 functions from a total of 77,000 functions, and then we select 44 functions to apply step 2 and step 3 of our methodology, and we keep the remaining functions, the remaining 100 functions, to validate our methodology. Now we apply step 2 of our methodology to the selected 44 functions. We collect the expansion and temporal locality metrics from our applications, from these 44 application functions, and we perform a locality-based clustering. We use the k-mean cluster algorithm to create two groups of applications. So we have applications which have low locality, here in orange, and applications that have high locality, here in blue. The closer the benchmark is to the bottom left corner of this plot, in other words, the lower their spatial and temporal locality, the less likely is to take the application is going to take advantage of a deep cache hierarchy or other mechanisms, as for example, hardware prefetchers. Then with this cluster in mind, we conduce our bottleneck analysis, the step 3 of our methodology. So within these two groups of functions that we identify in step 2, we find we use the other three metrics that we use in step 3, arithmetic intensity or AI, less level cache misses per kilo instruction, and last to first miss ratio, plus the temporal locality that we obtain in the second step to classifying the memory bottlenecks of a particular application. Based on these metrics, we find 6 classes of functions that suffer from distinct data movement bottlenecks. These classes of memory bottlenecks are the following. First, we have applications that are DRAM bandwidth bound. Then we have applications that are DRAM latency bound. We have applications that are bound by L1 and L2 cache capacity. Applications that are bound by L3 cache contention. Applications that are bound by L1 cache capacity, and applications that are not bound by memory. Those are compute bound applications. With such classification, we analyze how these functions in each class of each of the 6 classes of memory bottlenecks correlate with those three different data movement mitigation mechanisms in terms of performance and energy using our scalability analysis. Next, we will look in details about the scalability analysis for each class of memory bottlenecks, starting with the DRAM bandwidth bound applications. So applications in this class have low temporal locality, high last to first miss ratio, high MPKI, and low arithmetic intensity. So first, applications in this class 1A, exert high memory pressure in the system because of its high MPKI. It means that they will likely require high memory bandwidth from the memory subsystem. To understand how such high memory pressure impacts performance, we observe how performance scales when increasing the number of cores. So here in this plot, we have one of the application functions in our benchmark suite. In the x-axis, we have the number of cores for varying from 1 to 256, and in y-axis, we have the normalized performance of the application. The performance is normalized to the single core execution of the application. In the second axis of this plot, we have the DRAM bandwidth of the application. The RAM bandwidth that was provided or was exploited by the application. So as you can see from this plot, the host performance scales well until the memory bandwidth saturates at 64 cores. NDP, or in data processing, on the other hand, provides better scaling for this particular application since we don't have a saturation point for the memory bandwidth. So here in the plot, we have the same analysis that we did in the host system, while we have number of cores in the x-axis and the normalized performance of the NDP system in the y-axis, and we have the sustained bandwidth in the secondary axis. As you can see, the performance does not saturate because the bandwidth provided by the hybrid memory cube or the 3D stack memory does not saturate as we increase the number of cores. Therefore, we conclude that such applications in this class are DRAM bandwidth bound, and they highly benefit from the need data processing architecture because they can take advantage of the high memory bandwidth available within the memory device. Likewise, we analyze the energy consumption of these DRAM bandwidth bound applications when executing on the whole CPU system and in the NDP system. So as I mentioned before, these applications in this class 1A, have high less-first-miss ratio, which indicates that they can do not make effective use of the L2 and L3 caches. We observe how such inefficiency impacts the energy consumption for the system, for the whole system and the NDP system. So here in this plot, I have the energy breakdown of different components of the memory subsystem for one application in class 1A, while varying the number of cores. So we are going to make the following observations. First, as you can see in the figure, the host energy consumption is dominated by the L3 cache lookups and the high energy of the off-chip memory, off-chip DRAM requests, as we expected due to the high less-first-miss ratio. Second, NDP, on the other hand, reduces the energy consumption compared to the whole system, since it's going to avoid the L3 lookups. Remember, the NDP system only has L1 cache as its cache hierarchy, and also is going to avoid the costly off-chip memory traffic, since the computation now is moved inside the logic layer of the 3D chip itself. Therefore, we conclude that DRAM-bound applications highly benefit from NDP architectures when considering the energy consumption, since the NDP system does not access L2 and L3 and off-chip links, leading to large system energy reductions. Now you analyze DRAM-bound applications. Application in this class has low temporal locality, high less-first-miss ratio, low MPKI, and lower arithmetic intensity. Applications in class 1B do not make effective use of the cache hierarchy, since they have high less-first-miss ratio, but they do not exert high memory pressure on the memory subsystem, since they have low MPKI. We observe that even though the host CPU system scales well, the NDP performance is always higher for applications in this class. We find that the NDP system improves performance because it reduces the average memory access time of a particular application. So here, in this new plot, I have the average memory access time in cycles for a particular application in this class, broke down into the components of the memory subsystem while varying the number of cores for both the host and NDP configurations. We are going to make the following observations. First, the memory access time takes longer in the host CPU system than in the NDP system due to the additional latency lookups of checking the L2 and L3 caches, even though the data is rarely present in those caches, and going directly to the off-chip link. To conclude, this application in this class 1B, benefit from the NDP system, but mostly because of the lower memory access latency that the NDP system provides for the memory request that needs to be served by DRAM. These functions could benefit also from other latency reduction techniques, such as L2 and L3 cache bypassing or low latency DRAM. Now we analyze L2 and L3 cache capacity bound applications. The application in this class has low temporal locality, decreasing less-first-miss ratio, low MPKI, and low arithmetic intensity. We find that the behavior of the function in this class depends on the number of cores they are using. The decreasing less-first-miss ratio implies that L2 and L3 caches become effective when you increase the core count. So we analyze how this impacts performance. At low core counts, the NDP system outperforms the host CPU system. With low core counts, applications in this class have low to medium to high less-first-miss ratio and behave like class 1B functions, where the DRAM latency bound. As the core count increases, the host CPU system begins to outperform the NDP system. This happens because as the core count increases, the aggregate size of the L1 and L2 caches also increases in the CPU, the host CPU system, which reduces the miss ratio of both L2 and L3 caches. To conclude, we find that the primary source of memory bottleneck in class 1C functions are the limit L1 and L2 cache capacity. Therefore, the NDP system improves performance at low core counts, but does not improve performance as the across all core counts for class 1C functions. Next, we analyze.
Geraldo.
Yes.
Sorry to interrupt you. There are several good questions in YouTube. So the first one, it's asking about the LFMR. It says, in the classes classification, you divided the applications based on decreasing or increasing LFMR.
Yes.
Increasing compared to what?
Okay, it's a great question. So is increasing or decreasing compared with the core count? So when you increase the core count, we are also increasing the size of the private L1 and L2 cache, right? And since the last first miss ratio metric is calculated based on the L1 and L2 and L1 and L3 cache, so it's pretty much defining how much cache misses are being filtered throughout the cache hierarchy. This metric has the potential to change as we increase the cache size. As we increase the cache size, because we are increasing the number of cores. So some classes of bottlenecks, as class 1A, even though you are increasing the core count and the cache size, we don't see an increase or decrease in LFMR. It's constantly high, depending of the number of cores. However, as I just presented, for example, in class 1C, when you are increasing the cache size and increasing the core count, the last first miss ratio, it starts decreasing. So it starts quite high at 1 or something close to 1, and then it starts dropping as the number of cores increase. So it's increasing or decreasing based on the number of core counts. I hope it answered the question.
Yeah, I think so. That's a good answer. There is another question from Dimitrios. He's asking now about the MPKI. So what do you mean by high or low MPKI?
So yes, our definitions of high and low MPKI, we follow the same definition that prior works have shown. We observe that empirically in our evaluations, that application has high MPKI if the last level cache misses MPKI is larger than 10, and if it has low or MPKI if the last level cache misses per kilo instructions is lower than 10. So this comes both, this 10 value comes both from prior works that uses this as a threshold and our own empirical observations doing our analysis of these 345 different functions. So this is why it's high or low, and it's defined by this 10 threshold.
Exactly. You're also going to explain how you obtain this threshold now when you discuss the validation.
Yeah, when you discuss the validation, I'm going to explain that how you do the threshold for low, decreasing, high, the values for each boundary that defines a class is going to be explained later on.
There is one last question here in the YouTube chat. I think it's more related to the tutorial part of your presentation. But anyway, maybe you can already explain a little bit. So it's how do you obtain the AMAT time? Do you use ZSIM or Remulator?
So we use a combination of both. So we use ZSIM to simulate the cache hierarchy of the cores, L1, L2, L3, and we use that Remulator to simulate the memory the DRAM chip itself, in our case, a 3D stack memory. There are three main components, or four main components when you calculate the average memory access time, which is the L1, L2, L3 miss ratio, and also latencies, and also the DRAM average access latency. So the L1, L2, and L3 latencies and miss ratios we get from ZSIM as a metric that output from a simulation. And the average DRAM access latency we get from Remulator. So, yeah.
Okay, thank you for the answers, Geraldo. There are no more questions for now.
Thanks, Juan. Okay, so I'm going to talk about these high temporal locality applications, starting from class 2A, which are applications that are bottlenecked by L3 cache contention. So applications in this class have high temporal locality, increasing last first miss ratio as we increase the core count, low last level cache MPKI, and lower arithmetic intensity. The increasing last first miss ratio with core count indicates that the L2 and L3 caches become inefficient when you are increasing the core count. We observe that we are going to observe how much this inefficiency is going to impact the host NTP performance. So a low core count the functions do not benefit from the NDP system. This is because at low core count, these functions make reasonable good use of the cache hierarchy. Remember, these applications has high temporal locality. However, when you increase the core count, the whole CPU system performance starts to decrease and being outperformed by the NDP system or by the NDP cores. This is because these class 2A functions are bottlenecked by cache contention. So here I have a breakdown of the memory requests as we increase the core counts. And as we can see from this plot, at high core counts, this cache contention reduces the cache efficiency and causes the less plus minus ratio to increase to near to 1, thus increasing the number of memory requests that needs to be served by DRAM. With the less level cache becoming essentially inefficient, the NDP system greatly improved the performance over the whole CPU system. So basically here we have the classic problem that you are scaling up the system, increasing the number of cores. We have a private L3. And since we have this, we have the shared L3, and then we start to create either a problem of contention in this shared L3, or a problem of cache trashing in this L3. So because of that, the L3 miss ratio starts to increase, and more requests needs to go to DRAM, and then impacting the performance of the whole CPU system. So we conclude that applications in this class are bottlenecked by cache contention, and at high core counts, those high locality applications becomes basically DRAM latency bound. Next, we analyze applications that are bottlenecked by L1 cache capacity. Applications in this class have high temporal locality, low less first miss ratio, low MPKI, and low arithmetic intensity. The lower less first miss ratio in PKI and high temporal locality in these applications indicates that such applications make effective use of the cache hierarchy and also have low memory intensity. Also, their low arithmetic intensity indicates that such applications execute few operations per bytes loaded from the main memory hierarchy. For the memory hierarchy. We observe that the host performance and the NDP performance scales in a similar fashion, even though the NDP system has way less on chip caches. Recall that the NDP system only has a private L1 cache of 32 kilobytes, while the host system has a deep cache hierarchy with L1, L2, and L3 caches. So such reduction in SRAM size does not hurt performance, since that L1 cache present in both host and NDP system dominates the average memory access time for such applications. We then conclude that even though the NDP system does not mitigate any memory bottleneck for these applications, it can still be useful to reduce the overall SRAM size in the future systems. Finally, we analyze compute-bound applications. Application in this class has high temporal locality, low less first miss ratio, low MPKI, and high arithmetic intensity. Similar to the previous class that I just talked about, the low less first miss ratio in PKI and high temporal locality shows these applications are going to make good use of the cache hierarchy. However, different from class 2B applications, this application has high arithmetic intensity, which indicates that such applications execute many operations per byte loaded from the main memory. You observe that the host performance is always greater than the NDP performance for such applications, since these applications highly rely on the L2 and L3 caches, which are not present in the NDP system. We conclude that applications in class 2C do not experience large memory bottlenecks and are not a good fit for NDP offloading in terms of performance. We have an analysis in the paper regarding energy. To conclude, our scalability analysis leads to our 6 different classes of memory bottlenecks. Sorry, I have animation. My computer froze. Yes. So it leads to these 6 different classes of data movement bottlenecks. And we invite you to check our paper for a comprehensive discussion about the performance and energy scalability of each one of those 6 memory bottlenecks classes. Next, we are going to validate the accuracy of our workload characterization methodology on a large set of functions. To this end, we are going to apply a 2-step validation methodology. To do so, we are going to first apply step 2 and step 3 of our methodology, memory bottleneck classification, to the remaining 100 memory baud functions that you obtain in step 1. Then we are going to provide this two-phase validation. In the first phase of our validation, we are going to calculate the threshold values that are going to define the low and high boundaries of each one of those four metrics we use during the clustering of the initial 44 functions into those different 6 classes of data movement bottlenecks. We also include the last first miss ratio curve slope to indicate when the last first miss ratio increases, decreases, or stays constant when we scale the core count of the system. In phase 2 of our validation, we calculate the accuracy of our workload characterization by classifying the remaining 100 memory baud functions using the threshold values you obtained from phase 1 and the last first miss ratio curve slope. After phase 2, a function is going to be considered to be accurately classified into a correct memory bottleneck class if and only if it fits the definition of the assigned class using the threshold values obtained from phase 1 and follows the expected performance trends of the assigned class when the function is executed in both whole CPU system and in the NDP system. By applying such validation methodology, we find that we can accurately classify 97% of the 100 memory bound functions into one of the 6 memory bottleneck classes. We expect that the accuracy of our workload methodology can be further improved by incorporating more and more workloads into our workload suite and fine-tuning each metric to encompass an even larger set of applications. We invite you to check our paper for further analysis and discussions, including a study on how increasing the size of the last level cache impacts our workload characterization, from where we see that only very large L3 cache sizes, as large as 512 megabytes, can mitigate some, but not all, cache contention bottlenecks. Also, we have a summary of our workload characterization, include our load characterization, that uses in other core for the whole CPU system and for the NDP system. Also, we explain the limitations of our methodology and also analysis of the diversity of our benchmark suites. All of that, again, can be found in our paper. Finally, I'm going to briefly talk about our case studies in our work. I'm going to stop quickly to see if you have any questions before going to the case study. Juan, do you have any questions?
No, I don't have any questions. I think you can continue.
Okay. Thanks, Juan.
Oh, wait, there is one question. Give me 1 second. Okay, yeah, this is, I'm going to read it. It says, even in compute-bound applications, if the host CPU and the PIM cores are identical so that they have the same computational power, why host performs best at 2B and 2C? Is it reading from L2 still faster? It's still faster than reading from HMC in the PIM application? Yeah,
it's a good question. Yes, so reading for L2 is still faster than reading from HMC or a 3D stack cache memory. So a common latency of a L2 cache, a 256 kilobytes L2 cache, is around 7 CPU cycles. If you consider that the CPU cycle is I don't know, 2 gigahertz, this is, let's say that is 8, and then it's like 4 nanoseconds. So it's quite quick. Accessing a memory like HMC, HMC provides a bunch of bandwidth and reduce some of the DRAM latency, but is still fundamentally DRAM, which is still pretty low, high latency compared to SRAM. So average access latency. So if you think about only the raw access latency of HMC, TRCD, this is around, if I recall correctly, 20 nanoseconds. So it's much higher than accessing the L2 cache. This value is even this 20 nanoseconds, I think it's 19 something, 19.2 if I'm not wrong, or something like that. This value is lower than the access latency, the access latency of regular DDR4 memories, which this value is around 30, 34 nanoseconds, but it's still quite larger than the SRAM buffer. There are other technologies that are more promising, like monolithic 3D architectures, where in some designs you might have a main memory device which has lower latency than a SRAM-based L2 cache. But this is more like I don't want to say futuristic, but under study type of setup or a research proposal. It's not even though PIN is still, but we have industrial proposed, but from the technology that are mature enough today, SRAM and DRAM, this is the case. SRAM is still L2 SRAM cache is still much faster than DRAM memory, even if you consider a 3D stacked DRAM memory. So this is exactly why this is happening.
Thank you, Geraldo. I think it was clear.
Thanks, Juan. So, okay, so I'm going to enter the case studies now. So there are still many open research questions related to NDP system design, including, for example, interconnections, how to design good interconnections, how to do data mapping allocation for NDP systems, how to design the NDP core of the system. So it should be accelerator, or it should be a general purpose core. Sorry. What is the most appropriate offloading granularity to offload to the NDP cores? How to do programmability of the NDP cores, how to maintain coherence, how to do system integration, and much, much more. So if you are curious about open research problems in NDP system designs, I heavily suggest you to check our paper called A Model Primary Processing Memory, which is linked here or referenced here. All of those problems are described over there. So our goal in these case studies in the DAMOVE paper is to demonstrate how DAMOVE can be useful to study some of those system design problems. So we present 4 case studies in the paper. And I'm going to give a quick overview about each one of them. So the first case study, we use DAMOVE to evaluate the interconnection network overheads that NDP core placed on the different vaults of 3D stack memory is going to suffer from. So we observed that a large portion of the memory requests of the NDP core go to remote vaults, which increases the memory access latency for the NDP cores. We believe that DAMOVE can be employed to study better data mapping techniques and interconnection networks designed to aim to minimize the number of remote memory accesses in an NDP core, and also better interconnection networks with lower interconnection network latencies. The second case study, we evaluate how the benefits of NDP accelerators can provide for 3 applications for our benchmark suite. So we compare the performance improvements of an NDP accelerator against the compute-centric version of the same accelerator. We observed that the NDP accelerator provides significant performance benefits compared to the compute-centric version of the same accelerator for applications in class 1A, 1B, but does not provide any performance benefit for applications in class 2C. We believe that DAMOVE can aid the design of the NDP accelerator that targets different memory bottlenecks in the system. In the third case study, we perform an ISO area and power performance evaluation to compare NDP systems using in-order cores and out-of-order cores. We observe that in-order cores performance benefits for some applications are limited by the core static instruction scheduling mechanism. We believe that better NDP systems can be built by leveraging techniques that can enable dynamic instruction scheduling without incurring the large area and power overheads of out-of-order cores. DAMOVE again can help in the analysis and development of such NDP architectures. In the first case study, we evaluate the benefits of offloading small portions of the code, as for example, a basic block to NDP, which simplifies the design of the NDP system. We make observation that many applications, a small percentage of the basic block is responsible for most of the last level cache misses for that particular application. By offloading such basic blocks to the NDP cores, we observe that we have a performance improvement of up to 25% compared to the CPU system. We believe that DAMOVE can be used to identify simple NDP instructions that enable building efficient NDP systems in the future. Again, we invite you to check our paper for more details about each one of these case studies. So we open source the move to facilitate further research in mitigating data movement bottlenecks, including new data processing architectures. So here I have a screenshot of our DAMove repository, where we can find the collection of these 144 application functions that have composed our benchmark suite, and also our DAMove Sim simulator. And to get this, you can just check our Safari GitHub, or just clicking this link. So, so before I conclude, I'm going to see if we have any new question, Juan.
Yeah, Geraldo, I don't see any new questions for now.
Okay, great. Thank you. So I'm going to conclude this talk. So the problem that we are dealing in this paper is that even though data movement is a major problem in modern systems, it's still unclear how we can identify in a methodological way different sources of data movement bottlenecks, and the most suitable data movement mitigation technique that can solve the particular data movement bottleneck. So the goal of this work is twofold. First, we want to design a methodology that can identify different sources of data movement bottlenecks, and also want to compare how compute-centric and memory-centric data movement mitigation techniques can alleviate such data movement bottlenecks. The key approach that we take is to perform a large-scale application characterization to identify key metrics that can reveal the sources of data movement bottleneck over a large set of applications. The key contributions of this work are we have 4 main contributions in this work. First, we have these experimental characterizations of over 77,000 functions across 245 different applications from varying domains, from where we develop a methodology that can classify the applications based on their data movement bottlenecks, the source of data movement bottlenecks, and their relation with different data movement mitigation techniques. We provide also DAMove, a benchmark suite with 144 functions that can be used for the study of data movement bottlenecks. And we also show how DAMove can be useful in open research problems with 4 case studies. Again, DAMove is open source and is available already in our GitHub repository. So this concludes this part of my talk before we enter the tutorial part. So I don't know if there is any question from the audience, from Zoom.
I don't see any questions. Geraldo, maybe you can go to the next part.
Okay, so I'm going to briefly explain how you can use DAMove Sim and DAMove benchmarks to do research and collect metrics. So this is the outline for this tutorial part. So first, I'm going to show how you can download and install our benchmarks and also our simulator. I'm going to show how you should compile the workloads, you should install DAMove Sim, how you can generate configuration files to run simulations, and how you can finally run simulations and collect metrics. So first, start with downloading and installing. So this is quite straightforward. So first, just need to clone the DAMove GitHub repository. And after you clone the repository, you're going to find the following files over there. The most important one to get the workloads is the script called get workloads. This get workload repository is going to be the one that is a script to download all workloads, because this DAMove benchmark suite is quite large in terms of size. It's around 9 gigabytes. So we split it in different parts. So we just simply run the get workload script. The get workload script are going to automatically download each part of the workload, the benchmark suite, decompress and place it accordingly over the directory. And after that, we are going to you can see the benchmarks that you have in DAMove Sim. In DAMove, sorry. It's important to say that the DAMove benchmarks is a collection of popular benchmark suites from varying domains. So it's important to say that the license of each one of those benchmarks is still apply over here, and you can check each folder to see if the license or the compilation or the dependencies of each one of those benchmarks. So now to compile the workloads, so we provide a set of scripts to facilitate compiling those workloads. But before, I have some notes that is important to say. As I said, that moves a collection of benchmarks from other benchmark suites. So each workload might have its own set of dependencies. So we reference the user to the README of a particular benchmark suite to see if you are missing any dependence. And inside the directory of each one of the benchmark suites, you're going to find a Python script called compile that you execute. So for example, here I have stream benchmarking or workloads in the move. So if you go to the workload stream directory and you just type Python compiler, you are going the script is going to automatically compile the stream workload and also generate the independent binaries for each one of the function of interest that was identified in step 1 of our methodology. So when you execute stream, for example, we found that there are 4 functions that are interesting for us to evaluate. Those are stream. Those are, if you open the stream benchmark suite, it's going to be add, copy, scale, and triad. And the script is going to compile the benchmark suite and then place all of those 4 different binaries on the directory. Is again, the script is going to generate a single binary per memory bound function. In this case, this is important to facilitate simulation. So if you want to simulate a string, for example, you don't need to just simulate. You don't need to simulate one function per time. You can simulate all of the functions at once, speeding up the simulation process. So to install the move, so installing the move is also quite straightforward. We provide a setup script that is going to download all of the dependencies for ZSIM and for RowHammer, which are the basis of the move sim. And after that executes correctly, you just run the compiler script, and after that, everything should be properly compiled. And to execute a simulation, again, this is based on ZSIM. You just run build-up the ZSIM and a configuration file. And next, I'm going to show how you should generate this configuration, how you can generate such configuration files. A configuration file pretty much defines the system that you want to simulate. So to generate the configuration files, we also need to understand which systems you want to simulate. So the move sim simulates many different systems. For example, a host CPU system with private L1, L2 caches and a shared L3 cache with a fixed level cache size. We also have the host with prefetcher, which is the same as the host system, but includes a stream prefetcher in the simulation. Has a host with a non-uniform cache access or NUCA setup. So this is pretty much, again, the same as the host system, private L1, private L2, share L3, but now the L3 is organized in a 2D mesh network type of setup. And the size of the last level cache is going to increase as a factor of the core count. And also you have the near data processing core, which is the NDP system with a private L1 cache. So we provide sample template configuration files under this template folder, which enables you to simulate all of these system configurations that I just described. On top of that, we also provide an accelerator model to simulate NDP and host accelerators. So this accelerator is based on an accelerator simulator called Aladdin, and very much models data flow accelerator for a particular application. I'll refer you to the original Aladdin paper for you to understand how a data flow accelerator is built, but very much we model a similar design here in ZSIM. So after we have these template files, we have to create the configuration, the configuration files. But for that, we need to know how we need to execute the command lines to execute the application. So for that, we define a command file. This command file is going to have some fields. Those fields are the benchmark that you want to execute, the application within this benchmark, the function within this application, the path for the binary and the input for this binary that you want to execute. So here I have again some examples for stream. If you go to the command file files for the stream benchmark, you are going to have the stream benchmark switch, the function, the application that you want to execute, in this case add, the function in this case is also add, the path for the binary that was generated using the compiler compile.py script, and then the inputs in this case only have the number of threads that are going to be executed. Yeah, I just went through them. And we have command files available for all of the 144 application functions that we are providing in the move benchmark suite. Finally, we combine everything to generate configuration files. So to generate a configuration file, again, we provide a script called generate configuration files, which you pass as input the command files, the command file for the benchmarks that you want to generate configuration files for. After that script runs, you are going to have configuration files for under configuration files for all of those system configurations that I just talked about before. So the host accelerator, host using all the cores, host using all the cores, ping accelerator, ping all the core, and ping using all the cores. So here again, I have the example for stream. So if you go to the order for the cores, we have the version with and without prefetcher. Then we have the benchmark suites, the stream, and then we have configuration files for varying core counts for 1 to 256. And here, finally, the configuration for the different functions in the stream benchmark suite. So I'm going to give you a brief view of what is inside the configuration file if you want to modify it further. So this is a look of the configuration file. In the configuration file, you define the type of cores and the number of cores that you want to execute. This type of core can be out of order core, or means out of order. Time is a simple in order core, or the accelerator model that I explained before. And also you have the cache hierarchy, the organization of the cache hierarchy. So here it defines you can define the cache size and its organization, and also the path for the RowHammer configuration file that is going to be used during the execution of the simulator. Again, we are going to use RowHammer as the memory controller, and in this case here we are using HMC as the main memory device. Finally, we have some simulation probes that are important to set, or is already set by the scripts, but it's important to understand. The first one is the P modes, which can be true or false. So if it's false, you are running in a whole CPU system, so the cache hierarchy is going to be respected. If it's true, then you are running in the NDP mode, you don't have L2 and L3 caches. Also, the simulation, the number of instructions that you want to simulate. Often you want to limit the number of instructions because simulations can run for a long time. So we set, in this case, 1 billion instructions. When you reach to 1 billion instructions, we terminate the simulation. And finally, the command that is going to be executed or going to be simulated. So finally, executing the simulation. So after you generate the configuration file, if you want to run a simulation, it's quite straightforward. You just do build opt-sim, and then the path for the configuration file that was generated in the configuration file script. And this is going to run stream. This first example here is running stream using a host CPU, using out of order cores in a system without prefetchers, and we are using 4 different cores. After that, you can run the same simulation using an NDP system. So here I'm running stream using 4 cores in a ping using out of order cores. So a current limitation of the move sim is that we don't provide support for concurrent execution of both host and NDP cores. So this is why you need to execute first you execute the host CPU cores simulation, and later on you execute the NDP system cores configuration, and we are going to compare their statistics, but you need to run the simulation twice because of this current sim limitation. After you do the simulation, now you want to collect the stats to compare the execution. Statistics are stored under the ZSim stats folder. And you're going to see many different files over there. So here, for example, we have the DRAM request per phase. This is pretty much how many DRAM requests were done by the application per phase of simulation. This out.fg is just the dump of your configuration file. The actual important files are the remulator.stat and the zsim.out. The remulator.stat are going to hold statistics regarding the DRAM simulation. So queuing latency, number of memory DRAM requests, average DRAM latency, bandwidth, all of that is in remulator.stat. And that zsim.out is going to hold the statistics regarding the simulator or simulation of the CPU. So you have here the simulator instructions, how many cycles it took to simulate the application, the cache hierarchy performance, so L1, L2, and L3, and miss ratios and the latencies are all over here. So we provide also some script to filter the statistics, because if you open the stats file, they are quite large. So we have this get stats per app script. So pretty much you run the script together with the zsim.out file. And this is going to provide a summary of the execution. So here for the stream ads that we run before, you have here the summary, the number of instructions that was executed, the number of cycles that it took, the IPC or the instructions per second, instructions per cycle that the application reached, the L3 miss ratio, L2 miss ratio, L1 miss ratio, and the L3 MPKI, and also the last first miss ratio. And you do again the same, you run again the same script for the ping simulation. And based on these IPC numbers, you can compare the performance of both systems. In this case, you can see that the NTP system provides a speed up of 1.6 times over the CPU system in this case. Oh, sorry. So this is a brief tutorial on how you should run these simulations. This tutorial is heavily based on the README of the DAMove repository, so you can find it over there also. I guess Juan is going to post these slides online, and this slide should also be online on our webpage, so you can feel free to follow them if you wanna use DAMove sim, and feel free to fire me an email also if you have any question of any problem, or post an issue in the issue part of the GitHub repository. So over time you go over them and try to answer them as quick as you can. So thank you so much for listening.
Thank you very much, Geraldo. Very good talk. I don't see any additional questions in the YouTube chat. I don't know if there are any questions in Zoom while our students think about possible questions. I would like to ask you something. So your methodology has characterized the workloads in a, let's say, trying to be architecture independent, right? And so could you comment a little bit on what would be needed, what would you need to change if you want to target a more specific architecture?
So it's an excellent question.
I mean, architecture regarding both, right? On the host and on the PIM side.
Yes. So I believe the first two steps, step 2 and 3 are quite general or generic. So I don't think the second step would change at all, because this is architecture agnostic. It's just about the access pattern of the memory access pattern of the application. However, the third step could change. So in the third step, we have 3 key metrics per the scalability analysis. These three key metrics are the last first miss ratio, the MPKI, and the arithmetic intensity. So if you are, let's say that you want to characterize the film DRAM architecture, right? The film DRAM architecture is important to say that they don't have a deep cache hierarchy because it's just some float point units inside the DRAM chip itself. So what you could change, for example, is to have a better definition of arithmetic intensity. Our definition of arithmetic intensity is quite broad. So it's just operations. So any operation that is not a branch or is not a load and store is considered our operation here, divided by bytes. So here, the operations that actually matter for architecture like FIM-DRAM are float point multiplication operations, right? So you can include this definition of these operations into the arithmetic intensity metric to fine-tune that metric to the architecture that you are interested on. Likewise, for the last firstness ratio. So if you are considering this particular application in a system that does not have a L2 and L3 and L3 cache, maybe the system only has L1 and L2, so you can adapt the last firstness ratio accordingly. And MPKI, again, if the system does not have L3, you can directly use the number of memory requests that goes to that architecture. So by fine-tuning those metrics, and of course, the scalability analysis will change because the system that you are going to use are going to be different, right? It's going to be not the general purpose NDP system that you have, would be a FIM-DRAM system. So you can, based on this change, you can characterize if our particular application would benefit or not for this FIM-DRAM architecture, for example. Likewise, for UpMem. So something that is really important for UpMem, something that is really important for UpMem is the, as you explained in previous lectures, are the type of operation that we're executing. If they are integer operations, or if they are float pointing, and if they are float pointing multiplications. Again, you can break down the arithmetic intensity metric that you have here to further encompass these differences, and then better characterize the data movement, the computation pattern of a particular application, and see if you're going to fit the UpMem. And also in the UpMem case, another important thing is communication, right? Every time you need to communicate across different DPUs, you need to go through the host, which is bad because it's costly. So the last firstness ratio could be another good metric to say if you are communicating too much over a less L3 cache in a whole CPU system while you're doing the profiling. So that could also give you a good indication if the application would benefit or not to a, let's say, straightforward, not program heavily program expert rewrite the code, like if you just port the code to the UpMem system, if that would work well or not. So to conclude, what I'm trying to say is that all of those metrics that we have over there, they are general because we want to generally characterize these systems, but they can all be fine-tuned to indicate, to better indicate the NDP system under study. Hopefully I answered the question.
Yeah, I think so, Geraldo. Thank you very much for the answer. There is one more question I can see in the YouTube chat. I'm not sure I understand the question completely, but maybe you can comment on it. Dimitrios says that he has used the move with the benchmark suite to reproduce many of the experiments. And he's asking if I wanted to extract more speed, for example, for the stream math function, what change would you focus? Changing the offload granularity, for example?
So if you want to do something for stream application, what you should focus is the number of, in the NDP side, right? The number of cores, all the cores are fine, and the bandwidth of the device. Maybe you can change the model, the simulation to increase the bandwidth of the HMC system. And this way you are mimicking something, or change the configuration to have something like HBM, for example, HBM 3 or something, because it's projected that over time, the number of layers and the number of these 3D stack chips are going to increase, and the bandwidth also are going to increase. And an application like Stream, which fits in class 1A, which has DRAM bandwidth bound, basically benefits for more bandwidth. So if you want to extract more bandwidth from a bandwidth bound application, you pretty much need to either find a way to increase the bandwidth utilization. In the plots that we have in the paper for the particular for the stream application, the NTP plots, you see that the curve does not saturate. So you reach to 256 cores, and the performance curve is still goes up without reaching a knee point. So if you increase that point to 512 cores, this is you're going to further improve performance for the stream application. We did the experiments ourselves inside internally, and we saw that if you increase it further to 124 cores, then you see a drop. Then the bandwidth of the NTP cores saturated. So basically, if you continue increasing the number of cores for this DRAM bandwidth bound applications, we can further improve the performance until we reach to a saturation of the internal bandwidth of the NTP system. And after that point, basically, we need to find a way to improve the bandwidth of the provided by the memory device itself, either by moving to another memory technology or artificially change the bandwidth by change the I/O frequency or something like that. So hopefully I answered the question.
Yeah, I think so. Thank you very much for the answer, Geraldo. Okay. Yeah, is there anything else? Do you want to add?
So I think I said everything. Feel free to contact me if you have if I didn't answer your question about how to improve the simulation. We can discuss that over email. And yeah, so we are continuously working on improving the move simulator. So hopefully soon you are going to fix some of its limitations. And I just hope it's useful for people that are doing research in this area.
I think so. I think it can be useful to many researchers in the area. It's actually very nice tool and benchmark suite. Thank you very much again, Geraldo. I don't know if there are any other questions from our students. If not, I think that we will be done for today. Maybe we will have you again in a later lecture.
Probably so.
Okay, thank you again. Thank you everyone for your attention in YouTube, in Zoom, and again, Geraldo, for the nice talk.
Thank you.
See you all next Tuesday.
Bye-bye.
Bye-bye.